I know there were some technical issues so that we didn't have a projector, so I don't want to skip over it too fast. I want to make sure that we understand what's going on. It works. Yeah, it works. Perfect. Circuit, and I'm going to ask you guys to find the equivalent resistance for this circuit. Okay, so we have your battery here. And we're going to call these all 1 ohm resistors. Okay, so the activity here is to find the equivalent resistance. I'll work at it with you guys, but I want you guys to work on your own for now, okay? So I'll give you guys 5 minutes, work on this, try to get started. My reminder to you is try as best as possible to get rid of the series circuits first. Once you get rid of the series circuits, see what kind of parallel ones are enclosed within one another, and then try to get rid of those until you get more series. And then in the end, you should have only one resistor, one circuit with one resistor, okay? So do that. Maybe 5 minutes or so. Is Caralia here today? She's not. And Gabriela? No, she's not here either. Is that the only people I'm missing? Anyone know if she feels better, Gabriela? Who talks to her? No? Gabriela? No? She was here on Friday? Okay. So we're just doing the equivalent resistance of this. Okay, so let's go over the answer real quick. So what I did here is I took these two resistors because they're in series and I added them up together. These are in series, so I added them up together. These are in series, I added them up together, and these are in series, so I added them up together. So I did all four of those in one step so that you can see that my two ones here gave me a 2 there. Each of these add up regularly, so 1 plus 1 is equal to 2, 1 plus 1 is equal to 2, so there they are there. And I added these two up, 1 plus 1 is equal to 2, and there it is there. Now I have a bunch of parallel circuits, and these two are parallel to each other, and they're not affecting any other resistor. And these two are parallel to each other, and they're not affecting any other type of resistor. Yeah. Exactly. And but there is like a separation of a separation. So if I were to draw something like this, all right, and these all combine together and we keep going. All right. So in this case, which resistors would you do first? Let's number them off. 1, 2, 3, 4. Which one of these would you do first if I were to give you something like this? Yeah. You would do these two first, okay? Remember in, I guess it's grade 7 right now. If you did like 1 plus 3 times open bracket, 2 plus 3 close bracket plus 5 times 2 close bracket, close bracket, close bracket, right? It's kind of like that. You always do the innermost brackets first, okay? And that's the same thing with these circuits. You always do the innermost smaller type of parentheses or parallel circuit parts first. Okay, so perfect. Then what I did is I combined these two that were in parallel, these two that were in parallel, and I got an equivalent for these two together, so that's here. And for these two together, I got what's here. And then now they're all in series, I added them up, and I have one total resistance here. Yeah. Oh, it's this one here. All right. Any questions on that? That should be pretty straightforward. We need to know how to do this in order to understand today's lesson. So let's move on. So yeah, so today's lesson is going to be on Ohm's law. And Ohm's law is, I would say, the most important circuit law that you guys need to understand for this part. Okay. So how many laws is that so far that we have together? We have Coulomb's law, we have Gauss's law, we have Kirchhoff's law, and we have now Ohm's law. Okay, we're adding to our laws. Isn't physics fantastic? And Ohm's law dictates what this is going to have to do with voltages and resistance and current. And I'm sure you guys remember it. It's dictated by this equation here. V is equal to the resistor times its current. All right. Now this could be used in multiple ways. I'll just give you guys a second to write that. So V is equal to Ri could be used in many different ways. I'm going to talk about two of them. The first one being that you can say that the total voltage of the source, all right, is equal to the equivalent resistance multiplied by the total current. Okay? And I'll give you guys examples of what this means. That's an I here, by the way. It's just being hidden by the line. It could also be the voltage of just one resistor, right, is equal to the resistor's resistance multiplied by the current of that specific resistor. Okay, so I can use it for the whole circuit, or I can use it on individual circuits. Okay. So I'm just going to write that here underneath. So this is going to be for the whole circuit. And this one's going to be on individual resistors. All right. What is the relationship between voltage and current in this case? If I were to graph the relationship between voltage and current, what would it look like? Cedric? Yeah, let's just be a straight curve. Just like that. And the slope is going to be equal to R. All right. Now this is important because it only works for resistors. And light bulbs, as you've learned them in high school, are also resistors. But what we're going to do now this year is going to be working with LEDs. And LED lights are light emitting diodes. They're kind of like light bulbs, but not regular types of resistors. Because if you were to look at this relationship, it's actually exponential and it looks kind of like that. Okay? We don't need to know about that right now, but just please, please, please keep that in mind. And that you can't get a linear relationship between voltage and current when you're talking about light emitting diodes or LED lights. Okay? You guys know what LED lights are? Yeah, I'll explain to you guys how they work, but just to know where you get them, they're pretty much like the most standard type of lights right now. These ones here are fluorescent. They don't work the same way as the luminescent ones, which maybe your parents are used to, but you guys are the generation of LED lights. Right in this room, what could you tell me that's LED generated? Was that? Yeah, my screen is LED generated. What else? What's that? These ones are fluorescent, so these ones aren't LEDs. The projector is not an LED, but it's a really powerful regular light bulb. There's a special kind for that one. Yeah. What about your cell phones? LEDs. Yeah. So they're basically used in all screens now, and all the high quality screens are using LED. The generation before, the TVs were made up of LCD, which was liquid crystal display, and that works a little bit differently. But LEDs is light emitting diodes, and they're super, super energy efficient. Actually, so did I talk to you guys about this? The energy efficiency of LEDs? No. So in fact, like a regular light bulb is measured in watts. Its power is measured in watts, and that's the amount of energy it uses per second. That's what the unit watt is, joules per second. And if it's 60-watt light bulb, then that light bulb consumes 60 joules for every second that it's turned on. And then we use that to measure its brightness as well, because a brighter light bulb will use more energy per second. So a 100-watt light bulb will burn 100 joules per second, and that might not mean much to you right now. But if I were to tell you that an LED bulb for the equivalent brightness of a 60-watt light bulb uses 3 watts, so 3 joules per second. So that's 20 times less energy consumed for an LED light for the same brightness as a light bulb. And that's pretty important because you save a ton of money on electricity. Any one of you guys live alone right now and pay rent and pay for their electric bill? No, not yet. Okay, soon you will, and you'll have to pay for electric bill, and you'll see that number that you get is crazy high. And our electricity, as cheap as it is compared to the world standards, it's actually still quite expensive. And saving money on using LED bulbs becomes quite affordable. One issue that there is with LED bulbs is that to buy them, they're really, really expensive. So they're like $6 for one light bulb, whereas you can get like 3 regular incandescent light bulbs at a dollar store for a dollar. But their lifespan is so short compared to LEDs. LEDs are 100,000 hours. They're rated for 100,000 hours. And 100,000 hours is like, I would say like 10,000 times more than a regular incandescent light bulb lifespan. So you end up saving over a long period of time, not only on energy costs, but on the incandescent ones burning out energy. Plus, the government gives you a subsidy for how much LED bulbs you use in your house. So if you check off that box in your income taxes, you get a tax break for being energy efficient. Yeah. My parents will never understand that. They're like, oh, it causes cancer. It doesn't. They think everything new causes cancer, and you should definitely be using it. Okay. Any questions about this? No. So we're going to use that. What we need to know is that for our plugs here, they're 110 volts. They're also considered to be direct current. We'll explain what the difference between direct and alternating currents are. Do you guys ever hear that term AC/DC, other than the metallic, not the heavy metal band? AC/DC stands for alternating current, direct current. Our plugs use AC current, but we have a whole bunch of converters that that convert that AC current into DC current, and we'll learn about that. They're called diodes. Okay, yeah. So yeah, I was saying, when we plug something into the wall, we get 110 volts constant. All right. So if we need something at 110 volts, we get 110 volts from it. We can draw. We will draw always 110 volts, but we can decrease that with adapters. So your computers, for example, if you were to fry them with 110 volts, 3 amps coming into your computer, you'll destroy them. That's why you guys have those power block adapters, is to limit the amount of current that's coming in from the wall, and so that your computer doesn't get damaged. For all intents and purposes, we control the amount of current that we get from the constant voltage, right? So we control current, we control the amps that we get from a plug, and the voltage is constant. Okay, that's how it is in North America. Now, other places in the world might be different, but for the most part, your voltage is constant with your current change. So how we control how many amps we get so that's to not fry our things? Well, we use resistances. Okay, so the more resistors we use, the less current is going to flow through our appliances, and the less damage they cause. Okay. Any questions about that? So we're going to do these complex problems now, and there's like some steps to follow. The steps to follow are always going to be to find the total current first. Okay, so the reason why you're finding the total resistance is to find the total current. And if you have the total currents, then you can work your way backwards to solve what's the current going in each resistor. Okay, so ultimately the goal of this is to have a circuit, understand how much current is going through each resistor, and what is a voltage drop against each resistor. So let's do an example here. I'll wait until, is everyone done writing what's here? No? I'll wait a couple more seconds. What's that noise? Weird. Like someone's playing tambourine. Okay, so let's start this first circuit, and we're going to do this one together, and then the next ones you guys will do together with your tables or whoever you're sitting next to. So here, what's important is that the total voltage or the voltage of the source is equal to 30 volts. All right, that means that when a current leaves here, it has a potential of 30 volts, and when it gets back, what is its potential? 0. Okay, that's going to be the most important part. We have to make sure that whatever our circuit does, that it loses all of its voltage when it comes back. First, let's find the equivalent resistance. So what are you going to do first? Are there any resistors in series here? In series? Are there any in series? Which ones? What's that? There will eventually be a series one, but right at the moment there isn't. So these three are in parallel. So we can add those three up together. It would be 1 over 18 plus 1 over 9 plus 1 over 6. And that's equal to 2, 3, 6 over 18, 18 over 6. So is it 3? So I can remove this now. I can remove all three of those resistors and then put a single resistor here valued at 3 ohms. And now I have some resistances in series. So I can add those together. So if I were to add them together, it would be 15 ohms. Okay? So my next step would be, so first step complete, yes, awesome. We found the equivalent resistance. Now we need to know what is the current being drawn from my constant 30 volts. So remember, it's your resistance that determines how much current is being drawn from the voltage source. So in this case, I can use Ohm's law, and I'm using the one for the total circuit now. So you remember that the voltage of the source is equal to the Req times the total current. And in this case, it would be 30 is equal to 15 ohms times I total, and where I total is going to be equal to 2 amps. That's the total current that's going to travel through all of my resistors. Okay? Have you guys done this in high school? Yeah? Okay. So we don't need to do it, right? I can't make any jokes. All right, so I have this now. I have this total current, and I'm going to ask you guys a question. What is the current right here? Right here, or this arrow here? Yep, 2 amps. What is the current right here at the top right? What's that? 2 amps. You can say it louder, Elizabeth. I really like it when people answer. So you're doing halfway. You're doing it better than others, but still, I have to hear you. What about the current right here? 2 amps. Very good. I'm not going to worry about this this part here. This 3 parallel. What is the current here? Right here. Right before that 12 one. It's still what? It's still 2 amps. 2 amps. 2 amps. Okay. So remember, the amperage is the current, right? The current of water. And whenever the current is at its highest, it's going to be when there's the least number of separations. So all those 2 amps that I showed you guys right now, there was no separation. But over here, there is a separation between 3 different streams. But it doesn't matter because those streams are going to come together and form your original stream again anyway. So before and after those parallel parts of that circuit, the current was always 2 amps. Okay. Okay, so we figured out that here there is 2 amps. That goes through that resistor, that 12 ohm resistor. 2 amps go through that. So what is the voltage drop of my 2 amps going into that 12 ohm resistor? Well, we can figure that out because V is equal to R times I, and R in this case is 12 ohms. And this is what I was telling you. The second use of Ohm's law is to find it for individual resistors. We can do this. So it's 12 amps times 12 ohms times 2 amps. And that's going to be equal to what? How much? 24 volts. So if this resistor drew 24 volts from my battery, then that means that everything across this, from here to here, from that parallel point, is going to have to go from 0 to 6 volts. So 6 volts has to be given across this node here and this node here. You guys okay with that? What is Kirchhoff's law about voltages in parallel? They're the same. So that means that if there's 6 volts across those nodes, then it's 6 volts here, 6 volts here, and 6 volts here. Kirchhoff's law, remember, says that the voltages doesn't change when you're splitting your current up in parallel. Okay, the voltage is going to be equal across all of the splits in a parallel circuit. So if we know that each of those resistors in parallel there have a 6-volt drop, then we can figure out, using again Ohm's law, V equals Ri, you can figure out what the current is in each resistance. So let's do that. So here V is equal to Ri for this resistor, V is equal to Ri for this resistor, and V is equal to Ri for this resistor. So what's going to be the current going in each one? Now it's just a matter of math. So the voltage, the V is 6 volts. The resistance is whatever the value of the resistance is. And now you're trying to find the current. So it's getting a bit messy, so I'm sorry for that. If you were to calculate the currents individually, what do you notice about them when you add them up? Yeah, equals to 2. That means that 2 that came in got split up, and they came back together when they left that parallel part. But if you added them up individually, if they never did that split, then that makes sense, right? That all those currents would add up to the 2. So now we found the voltage drop and the current through each of the resistors in this circuit that is combined of parallel and series parts to it. Okay? You guys following? So let's do this one. You guys do it on your own. I'll pass around and check and answer questions if you have any. Let's not take too long on it. How many examples? Actually 3, 4. Yeah, we'll do all of them. Once you've done this one, go to example 3. Is everyone okay with what they need to do? No? Okay. Mhm. Yeah, if you find that that's 4 volts and that's a 12-volt battery and these are parallel, yeah, that's going to be D and that's going to be D. Okay, so you see that this is taking 3 out of 8. It's a proportion. So it's 3 out of 8 of that voltage, and this is 5 out of 8. So here, this one is separate from these parallel. So I would find what's going to happen first. Subtract this from 12, and that's what we go to the branch of the circuit. So once you figure it out, then you have the voltage that's across these 2 branches like that. And a matter of figuring out how much of the voltage will drop for each one. Well, at this point, all the current is coming back. So the total current is Everyone done number 3? Who is that? What did number 4 yet? Okay. Okay, so here's what's going to happen. For example number 3, I want you guys to work together with your tables and write up the solution on the walls. And if you get it right, then the golden bonus. Golden bonus is 1 point on your report card. 1 point. Yeah. For question 4. Right. Take your time. I'll give you guys enough time to work on it. This one here. The bonus is shared on the table, so everyone on your table gets it. No, everyone can get it. For something that's supposed to be group work, I don't hear a lot of talking. Isabel. Kevin, What did your group get for REQ? Okay, you haven't found the total resistance yet? Okay. I can tell you that you guys got it here. You guys too. Vous avez réussi le REQ. Le 178. I don't know, I didn't look at anything else. Yeah. I'll give you guys until 2:30, all right? 2:30. So this part of the this is PowerPoint number 14. So this part of the this unit is really short. It's actually only like maybe 10-15 minutes, and but it's really important to understand because you guys are going to be using LEDs in your circuits instead of light bulbs. and it's really important to understand how they work. So LED, you guys, if you've heard this term by now, it stands for light emitting diode. And the importantest part, the most important part of this LED is the D, which is a diode. Anyways, the fact that it's a diode. Now, the reason why it's important that it's a diode is that it does something special to the circuit. So, okay, basic functions and LEDs and all that stuff, we'll figure it out. So a diode is important in a circuit because uh, it acts kind of like a valve. Do you guys know what a valve is? What organ system of yours in your physiology uses valves pretty heavily? Which part? The vascular system? The circulatory system is the organ system that I'm talking about. The vascular system is just as good. Yeah, in your veins, in your arteries, or both, or in your heart, or where are these things? Where? They're not everywhere. There's some in the heart. There's some elsewhere. Where? In your legs? Which part of your legs? It's in the veins, okay, but not in the arteries. Arteries, for some reason, they don't have valves. Veins do, and your heart does as well. The heart has something called a tricuspid valve that's in your right right hemisphere of your heart, and then there's a bicuspid valve that's in the left hemisphere of your heart, and they control what? Why are these valves important? Why? Why? Tell me explicitly why. Yeah. Absolutely. It's to prevent backflow um, of your blood. Have you guys ever bought those Gatorade drinks where you have to like squeeze the bottle to get the liquid to come out? You guys know what I'm talking about? Like if you were to just hold that upside down, it would never flow out. You'd have to squeeze it to flow out. And that's like a valve. That thing there that's separating the outside and the inside of that bottle, that's literally what a valve looks like in your heart, in your heart and in your veins, and it is kind of, I mean, conceptually the same as what a diode is. So diode is exactly that. It prevents current from going against where it's supposed to go, and it only allows the current to go in one direction. So in this case, the current is allowed to go this way, but if the current tries to go this way, it gets blocked off and it stops the current, and it's kind of like a short circuit. So now at this point, the circuit is essentially cut, and there is no flow of electrons. Therefore, your circuit's not working properly. Okay. Um, you guys ever heard of, just because I'm talking about this and I feel like it should be mentioned, anyone ever heard of a heart murmur? Yeah, a heart murmur is someone who has a defective valve in their heart or maybe in their aorta and not in their aorta, in the pulmonary vein, sorry. And it makes it so that that defect makes it so that your blood somehow flows backwards. So you go pump, and you know how you, if you were to pump, and then you let go of the pump, you pump the heart, you press the heart to pump the blood out, then you let go, that heart is just going to suck the blood back in, right? And that's what that murmuring sound is, because the valve is dysfunctional. When you relax the heart, there's some blood that flows back, and it makes a special noise. And doctors are able to pick that up by listening to your heart through a stethoscope. They're not serious. A lot of people are born congenitally with these heart defects, and they're on the mild end of the spectrum of heart disease. I don't know, I just felt like saying that because it's important. All right, so here we have a very simple circuit. It's got two resistors, two LEDs, and the symbol for an LED is this, right? So let me just draw this symbol here. So this symbol, this red one that I just drew here, that's a symbol for a diode. You add those two arrows next to it, that becomes now an LED. All right, so this is the symbol for LED, and this is the symbol for a diode. Okay, and the direction of the arrow indicates the direction of the current that it allows. All right, so in this case, it allows the current to flow this way. In this case, it allows the current to flow that way. Okay, So that question is, which one of these, I'm just making sure I don't have the answer here. Okay, good. Which one of these two lights, the red one or the green one, is going to light up? Which one? Green one. Yeah. And that's counterintuitive because we know the electrons actually go that way, but out of convention, they go that way. And therefore, we assume that the convention of the drawing for the LED follows the convention of a circuit, and it does. And in this case, this one lights up, this one does not. Okay? So far, so good? Let's move on. So here's what it looks like, a regular LED. You guys definitely have at least two of these in your kits, maybe not, if not more. And I think you get multiple colors of these. And the way they work actually is the different voltages produce different colors. And there is an actual explanation as to which gas is released and which gas is in there so that the LED lights up a different color. There's always a positive and a negative end to the LED, and it's indicated by the short or long stem of the LED. Okay, so the long stem is always positive by convention. The short stem is always negative by convention. Okay, so if just take 2 seconds to open up your kits and take out an LED bulb, and just to make sure that your LEDs have two different length stems, and try to identify the positive and the negative. Now these LEDs, they have a short end and a long end so that you can determine what's positive and negative because they won't work if you put them the wrong way. Remember that, okay? And and in fact, if you set up a circuit, you'll notice that if you put it the wrong way, it just won't light up. And also, there's another thing that's super important about these LEDs is that they are super low voltage rated, right? So it means that let's say you power it with a 9-volt battery, which is what you guys have in your kits. If 9 volts of that, so if you connect that LED directly to your battery, definitely don't do that. If you connect your LED directly to the 9-volt battery, the voltage drop across the LED is going to be 9 volts, right? Because there's no other resistors. And the 9 volts is going to for sure flash your LED and it's going to burn out. You'll see a puff of smoke coming out and it won't work anymore after that and you'll have to buy a new one. These things are mega expensive. They're like 4 cents each. So, not expensive. So, I mean, don't worry if you do burn them. Tanya's got a whole bunch, but obviously she's not like a limitless supply of LED bulbs. Just try not to burn every single one of them. The reason why in this previous circuit there are these two resistors is because if I didn't have them, the voltage drop across each one of those LED bulbs would have been too high and it would have burnt out the light bulb for sure. Now, the way to tell what the voltage should be for that LED is by looking at the rating of the manufacturer. So you guys don't have that information at all. But I will tell you that it's pretty safe for anything below 3 volts. Okay, so 3 volts won't burn out your light bulb. You definitely don't want to go higher than 3.5 volts. Though at 3.5 volts, I think you're higher than any rated LED that exists, consumer level LED. So you don't want to increase the voltage too much. So that means you would put a resistor in front of it so that the resistor can take some of the hit, take some of that voltage, and so therefore the LED doesn't need to take as many. Does the resistor and the LED, do they have to be wired in parallel or in series, or it doesn't matter? You guys tell me. What do you think, Zach? It has to be in series. Why? That's how the voltage drops. Because if you have them in parallel, the voltage drop across the resistor and the LED is going to be that of the battery, and that's going to be too much for it. So you have to make sure that the resistor is signed up in series. What happens if your resistor is too strong, right? And the voltage drop across, you have a 9-volt battery, and the voltage drop across your resistor is 8 volts. How many volts is remaining to go into your LED bulb? 1 volt because they're connected in series. And is your light bulb going to light up? If yes, is it going to be dim or bright? If not, then why not? going to be dim, absolutely, right? So it's not going to have enough energy to light it up brightly. It will light up, but just not brightly. Yeah. Like this? That's a good question about circuits, not so much about LEDs. So let me explain that. It's actually a really good question that I never brought up. Let me see. If we go back to our previous PowerPoint when we were doing that one bonus question here, right? So if I were to show you this, so this current starts off going this way, and then it splits, and it goes down here, right? And then here it splits again, and then it reaches here. Where is it going to go after that? How did we know it's going to go straight up? It's not going to, well, yeah, because there's a current coming this way, so it's not going to interfere, but it could. There is nothing. If I had another battery here, or like if I had a battery here and a battery here, then there would be some interference. I mean, it's physically possible. Yeah, at this point, they have already lost all of their potential because they're basically, this might as well be the end of the battery because there's nothing in between stopping it. So your current's going to take the area of least resistance to go back to the battery. And that's exactly what's happening here. And if we go back to the diodes presentation, every time I start my PowerPoint, it brings me to presenter view. I don't know what. Okay. Yeah. So if the current goes down here, Cedric, where's it going to go after? It's directly going to go there because there's no more resistance in that direction. Okay. Good question. Any questions on the other ones? All right. So okay. So that's how the LEDs work. They need to have a resistor. So when you guys play with it later, make sure you have one connected. If your resistor is too strong, it's going to be too dim. If the resistor is too weak, what's going to happen? Poof. Yeah, it's going to be either too bright. I mean, there's no such thing as too bright, but it'll essentially overload and burn out. No, the voltage is like the current only it gradually intensifies when you have a situation like this. So it's not going to go all through the LED and then go into the resistor. It's going to figure out what it needs to do and then intensify that direction. Yeah, good question. Okay, so over here we have two circuits. One of them has something called a forward bias diode, and this one has a reverse bias diode. The picture is drawn backwards, but it should be drawn this way. Do I have it right? I think these drawings are drawn incorrectly. Hold on, let me figure this out for a second. Oh, the battery is drawn differently. Yeah, okay. So can you fix that, please? So just up here, this one should be positive, and this one should be negative. And just note that the battery is flipped around here. So in this case, the current is flowing towards the right, and the situation on the left, the current is flowing towards the right, and the diode is allowing it to flow in that direction. Whereas here, the current is flowing to the left, and the diode is pointing in the wrong direction. So what's going to happen in the second picture? Yeah, and it's going to be like if the circuit was totally disconnected. Okay, so it's not going to behave as a complete circuit without OD. It's going to behave as an incomplete circuit with an open circuit. Okay, so if you notice here, there is 0 volts across the bulb, and here there is 5.3 volts. What's important is that when the voltage is applied across the diode in such a way that the diode allows current, the diode is said to be forward biased. So in this case, the current and the diode are facing the same direction. We call that forward bias. And in this case, the current and the diode are facing opposite direction, and so we call that reverse bias. And I said that if you have a reverse bias diode, it's as if your circuit is closed, or sorry, open and then cut or whatever, but there is a specific amount of intensity known as the peak inverse voltage, where if you have that amount of voltage, whether it's forward or backwards, it's going to burn the LED no matter what. Okay? So will burn the LED no matter what direction. The representation of diodes can be quite different depending on where you look at. A lot of YouTube explanations on how to work uses PN junction representation that talks about this. The P stands for, what do you think the P and the N stand for? Positive and negative. So that would be the positive and the negative. And they're not charged. They're neutral, in fact, the P part and the N part until you apply a voltage to it. But what that is that there is these positively charged pocket, or not positively charged, but positively like influenced holes. They're called holes here. Then there are these negatively, there are basically electrons here. And these electrons and these holes basically come together. And when these holes come together, so these ones are going to go in this direction, and these ones are going to go in that direction. And when they meet, they release light, and that's your light emitting diode. Okay. I have a really crappy video. I don't even think I'm going to show it. It's like, I'll show it just to laugh at. Essentially, this is what I was talking about. So you have these energy pockets, and I call them holes, but what they are actually is like they're particles with low energy, positively charged sockets in them, right? So if they're low energy, it means that electrons definitely want to go into them because everything always wants to go at the lowest energy state possible. So the electrons that are going to flow from this end are going to try to meet up with those positively charged pockets, and when they meet, they reach a low level of energy state, and then they release light as a photon. So you can see here the electron falls into this pocket, and there's a lot of pockets, there's a lot of electrons, and they are attracted to each other. And then once they fall in together, there is light. Ta-da! So here they are. There's two plates. There is in this case that would it's not specified here, but one of these would be the positive junction, and this one would be the negative junction, and they would have that interface there. So far, so good. Here's what they look like, and you have a couple of them in your kits. One of them looks white, but they're actually green or red. They're not. They don't always have the color that they show. You have to light them up to see what color they are. And these are the wavelengths that you can produce. There are some new LED types that, depending on how much current you get through it, it'll light up a different color. That's amazing because it's the same bulb changing its color, and it's not like this. This is the examples of different bulbs being different colors, but there are such LED bulbs where they can emit different colors. They work with a different technology that I'm absolutely unaware of. And there's some text that I want you guys to read on your own time. And here we have an application, a really important application. You want to have a Mac with your charging? That's how you charge it? Charging? You have it? Right, so if you notice this Mac charger, this part here, it's got two of the same size slips. Okay? And if you look in your tables, look inside the little hole there, where there's the power outlet. So look at the holes where the two slits are going to go. And one of them is wider than the other. You guys notice that? Okay, that's because you always, some appliances can only, when they used to make them the old way, some appliances would have a large one and a negative one, so you can't plug it the wrong way. If you plug it the wrong way, the appliance doesn't work, right? And now what you have is inside these things, there's a whole bunch of diodes that make it so that the direction of the current is really not all that important, right? Regardless of which direction the current goes, it'll still work. So now they don't care about those size differences anymore, and they use the equally sized prongs in the adapters. Your phones probably have them. Even other computers probably. The ones with the grounds, normally they don't. If you have something that has a three-prong outlet, the two slits are going to be different size. That's not made because there was no diodes in them. That's just made because out of convention, they made to fit into all three of those holes in only one direction. But if you were to plug this in to the wall, whether you plugged it in like this or like this, it would still be the same job. Now, the reason for that is because I told you guys that these currents, every current that we get from Hydro-Quebec is a alternating current. Alternating current means, if I were to draw it, so here we have a regular direct current circuit, right? And we know out of convention that the electrons flow in that direction. An alternating current looks like this. And there is this symbol here instead of that battery. So they're both voltage sources. You can call this a 9-volt direct current or a 9-volt alternating current. And the difference is that this one is going to alternate. So you see how that looks kind of like a sine function? So if you were to look at the voltage, it actually goes like this. So half the time it's providing a positive potential and half the time it's providing a negative potential. That means that the current takes turns going like this and like this, right? And that's not good for certain things, like LEDs, for example. But it is useful because the way the energy is generated is through turbines. And anything generated through a turbine is going to generate alternating current electricity, right? And that's really good because using a turbine, we're harvesting the energy from the water flow. It's providing us with tons and tons and tons of amounts of energy. It has to do with magnetism, and we'll get to why exactly they give you an alternating current. But suffice it for now to say that the current goes in both directions. Now, that's not a good thing for, in this circuit here, for this load. Okay? So if this is an alternating current, okay, so it's kind of really the sine function diagram. So this current's going to go upwards and downwards. Now, if this were connected to a resistance, it would be horrible because the current's going to go that way, and the current's going to cancel out, and nothing is going to light up. So to fix that, we have something called a diode rectifier, right? And this makes it so that no matter how you leave the battery, no matter how the currents leave the voltage source, it's going to end up going into the resistance in one single direction, right? To remember, in this case, the battery or this voltage source doesn't have a positive or negative end. They're both positive ends and they're both negative ends. But the resistor or the load, this thing, does have a positive and a negative end. So let's follow what happens. If the current goes this way, all right, it goes in here. So which path is it going to choose, left or right? Right, all right. So it can't go left because the diode's facing the wrong way. And therefore, it's going to reach this junction. Then is it going to go through the bottom part or the top part? Top part, because the bottom part is not allowing it. So the current goes like this, goes down, goes up, reaches here. It could either go here and redo the same thing, or go here and then go down and come back. Okay? So far, so good? Now, what if the current, we started going in the opposite direction? So let's restart this whole thing. And then it went downwards. All right. Where's it going to go, left or right? Right. And here, up. And then it's going to go through the load. And then it's left to make the same decisions as before. Okay. So in this case, regardless of where my current is coming in from, the direction of the current is always going to go in the downwards direction on my load. All right, because if it were going backwards, then it would damage the load. Yeah, the load is like the thing that you want to power. Yeah. So yeah, Elizabeth. The load is going to have a direction that's going to be the only direction in which it works in. So most of our appliances only work under um, direct current electricity. That's why we have these rectifiers, so that we can convert the alternating current into a direct current. That's called a rectifier. So it's taking an AC current, turning it into a DC current. And it's as simple as using 4 diodes. That makes sense? I'll stop here. And we'll go over the test.